Good morning, good day, good evening, everyone. So it's 14 UT sharp, and let me start our webinar. The speaker today is Natasha Jeffrey. Natasha is currently a solar physicist. She is a researcher at the University of Glasgow. She is interested in a broad range of topics, but in particular, she is interested in using observations and modeling to determine properties of solar flare accelerated particles at the sun during solar flares. And today, Natasha will be talking about one of potentially very nice diagnostics of signatures of such particle acceleration. So please go ahead, Natasha.
Okay, thank you, Gregory, and thank you for the invite to talk. I hope everyone can hear me clearly. Please say if you can't. So yes, today I want to talk about detecting non-Gaussian EUV spectral lines at the sun, and how this might be a possible signature of either ion acceleration or processes that can cause acceleration, such as turbulence. So that would be an extra diagnostic alongside sort of traditional non-thermal line broadening. So before I start, I'd just like to mention some of my collaborators. So we have Lindsay Fletcher and Nick LeBras at the University of Glasgow, and also Michael Hahn and Daniel Savin at Columbia. Okay, so I will start with some basics. So we all know that UV/EUV line spectroscopy is a vital tool for uncovering the properties of solar plasma. So of course in flares and elsewhere. And most lines, of course, can be very well fitted by a Gaussian distribution. And this allows us to determine the first three moments of the line distribution. So the zero moment, for example, is the integrated intensity. And this tells us about ion abundances and electron densities, for example. And then we also have the first moment, which is the centroid position. And this can tell us about bulk plasma motions. The second moment is the variance, or the broadening of the spectral line. And for the type of lines that I'm talking about here, so optically thin, hot lines in the corona, this broadening should really be determined by temperature and basically the thermal motion of the ions along the line of sight. Now, of course, in solar flares and elsewhere, we often see line broadening that's larger than what we expect it to be. We see excess broadening. We often call this non-thermal line broadening. Now, for these type of lines, this can be due to extra plasma motions along the line of sight, so turbulence or plasma motions that might lead to turbulence. So in this sense, non-thermal line broadening is our prime diagnostic for studying turbulence at the sun. Now, if we look at a spectral line and it has a non-Gaussian line shape, for example, then we might have sort of extra diagnostic information. So the line shape in general should be determined by either the ion or the plasma velocity distribution along the line of sight. So as a simple example, if you have a Maxwellian distribution of ions, then their Doppler motions, their velocity PDF, will produce a Gaussian line shape. But if we have, say, random motions of non-thermal ions, then they should produce a slightly different line shape. And of course, we should be able to use this then as a diagnostic tool of these non-thermal ions, or possibly tell us something about the plasma motions. However, line profile analysis is not performed that often at the sun because it can actually be quite challenging. So, for example, many of the lines we observe might be blended, or they might have other lines located close by. So this means they're not suitable for a line profile analysis. They might have moving components, of course, and again, this sort of taints the line shape, and it's not suitable for a line profile analysis. Some instruments, maybe older instruments like the ICE, they have a very broad instrumental response, and the instrumental broadening can also sort of make the line shape analysis challenging, and we also assume that it's not producing maybe a non-Gaussian component itself. And then there's other things we need to think about, I guess. So the fitted wavelength range, spectral resolution, noise, background level, all of these different things could change our interpretation of the line shape. Okay then, so what is the best way of sort of detecting and then quantifying non-Gaussian spectral lines in the sun? Well, the best thing to do is to fit the line with some sort of profile that can detect changes in line shape. And we can fit the line there not with a Gaussian, but with a kappa line profile. Something of this form that I show in the equation here, which ultimately is derived from kappa velocity distribution. Now, the kappa line profile has, compared to a Gaussian, one extra fitting parameter, the kappa index. Now, the kappa index basically controls line shape. So if kappa formally goes to infinity, then we get a Gaussian line shape. Observationally, kappa has...
Natasha, in the denominator of your green circled formula,
yes.
Kappa 2 sigma square, what does it mean, kappa 2? Is it kappa square, in fact, or what?
No, I've just written it in an ugly manner, so it's like 2 times kappa times sigma squared.
It must be like that, yes, kappa times 2 sigma squared.
That's how I've written it here, yeah. You could write it in a different form, but yes, that's a 2 times, yeah. Okay, so, but if kappa is very small, so if we've got values less than 10, for example, then line shape sort of grows these large, broad wings and has a more peaked shape at its center, as you can see in the figure here. Now, I also want to point out that I'm using a kappa here to look at these non-Gaussian line shapes, but we're not necessarily saying that the underlying velocity distribution has to be a kappa velocity distribution. The kappa line profile is just a good way of quantifying the line shape. Now, also, I'm going to talk about a lot of Hinode ICE data here, and I should mention that in real life, things are more difficult, and what you actually fit to the spectral lines is some sort of convolved function that can account for the instrumental broadening as well. So what we actually fit to the spectral lines is a convolved kappa Gaussian distribution. So the kappa part of this convolved distribution is hopefully fitting the physical part of the line, and then we've just got that Gaussian there to fit the instrumental profile, where we're going to assume here that it is indeed Gaussian. Okay, so in the last couple of years, there have been a number of studies looking for the presence of non-Gaussian line shapes at the Sun, both with Hinode ICE and with IRIS. So there have been a number of studies looking at solar flares. So myself and colleagues at Glasgow, we looked at 2 different flares using ICE data, and we found non-Gaussian line shapes in 2 different spectral lines formed at different temperatures. And I'll talk a little bit more about that in the upcoming slides. There have indeed been interesting follow-up studies where a coronal source and a flare studied at the limb. Again, non-Gaussian line shapes were found in the hot IM24 lines there. Also, in other parts of the Sun, in non-flare inactive regions, studies have found non-Gaussian spectral lines are in the corona using ICE, and other studies have used IRIS to detect non-Gaussian spectral lines in the, much lower down in the transition region. And finally, studies have also looked at coronal holes at the base of the fast solar winds. Again, myself and colleagues did this, and we found very non-Gaussian line shapes in this coronal hole using Hinode ice. And again, if there's time, I'll talk a little bit about this at the end of the talk. Okay, so if we go on and think about solar flares now, let's sort of say something in more detail about the possible causes of these non-Gaussian spectral line shapes. So in a flare, for example, maybe these line shapes are caused by non-thermal solar flare accelerated ions, or maybe they're just caused by the plasma motions along the line of sight. So again, this could be another diagnostic of turbulence. And this could be very important. We know the important role that turbulence plays during a flare. It plays a critical role in transferring energy into accelerated particles and into heating. So having this extra diagnostic would be a nice tool indeed. Okay, so if we think a little bit more about solar flare accelerated ions, of course we don't have that much information about ions at the sun during a flare. We have a lot of information, of course, about accelerated electrons from the Bremsstrahlung X-rays that they produced. But a lot of flares, don't really produce much detectable MEV ion gamma ray line emission. And so often we have absolutely no information about accelerated ions at the sun. And these sort of EUV spectral line observations would tell us something about low energy accelerated ions. So if they're present, this would be helpful. So just detecting them would be a useful diagnostic. And then, of course, we could use them to say something about maybe energy associated with flare accelerated ions, and even use them to say something about the acceleration mechanisms in flares. So that would be one idea of this diagnostic. Secondly, if the non-Gaussian line shapes are due to the plasma motions, if they're due to turbulence, then it would be an extra diagnostic alongside non-thermal line broadening, in the sense that if you assume the turbulence produces a Gaussian line shape, then you're saying that the underlying plasma motions sort of undergoing Brownian motion, where you've got lots of smaller jumps about a mean. But of course, this might not be the case. So the velocity PDF of the plasma motions might produce more, excuse me, large sporadic motions about a mean, which could lead to different line shapes. And well, this needs to be thought about a little bit more, but sort of non-Gaussian turbulence in various forms is seen in space plasma physics. And again, I need to think about this more, but one idea would be if you were looking at different sort of velocity PDFs in different regions of the flare caused by these plasma motions that leads to turbulence, then maybe certain VDS, certain plasma motions would be more efficient at accelerating and transferring energy to particles into heating, for example. And that would be another very useful diagnostic in solar flares and elsewhere. Okay, so now I want to go on and talk about some results. So I'm going to show a flare example, an X-class flare that happened on the 29th of March 2014. This is a very well-studied flare because there's a lot of instrumental coverage. People have studied it for lots of different reasons. But we chose this flare purely because it has two very strong unblended spectral lines that were suitable for a line profile analysis. So at iron 16 and iron 23, which are both formed at different temperatures, so we can look for non-Gaussian spectral lines in different parts of the flare. So here I show the ReSi and GOES light curves. And next to that, I've got a nice image of the flare. So the background image shows the ribbons, basically. And then on top of that, you've got this red source, which is the coronal X-ray source. And then surrounding that, you've got these two blue sources, which are basically the hard X-ray foot points. And the nice thing about this flare is that we had ice data during the rise, peak, and decay phase of the flare. So I've got a little bit more information here for people that are interested in the ice observation. But the main thing I want to point out here is that, of course, there were lots of other wavelength windows, lots of other spectral lines that were available for study during this flare. But we only had 2 lines in this sort of IN23 window, which were suitable for a line profile analysis. And this shows sort of how difficult it is to perform this analysis for many flares. Okay, so here is one result. So, can you see that? Yeah. So here's one result. This is looking at the hot line of IN23, which is formed at a temperature of around 15 to 16 megakelvin. Now, this line was formed in this region where you can see the little rectangle on the solar flare. So spatially, it looks like it's next to the coronal source. Of course, we're unsure of the height from this image, but it's formed at a high temperature. So we can say that it's probably formed close to the coronal X-ray source. And next to this, we've got the spectral line, which comes from the small rectangular region. And please ignore the purple line in this figure and only look at the orange and the blue line. So the orange line is the Gaussian fit, and the blue line is the Kappa or the Kappa Gaussian fit. Now remember, ice has a very sort of broad instrumental profile, which sort of hides everything. But hopefully you can see that the Kappa Gaussian distribution, so the blue one, is able to fit both the wing and the peak very well in the spectral line. Whereas the Gaussian, it struggles to fit both. So here it's fitting the wing okay-ish, but it can't fit the peak. And we can see that the Kappa Gaussian is a better fit in terms of the residuals and in terms of the chi-squared value. And for this line, we get quite a small Kappa value of about 3.7, which suggests it's very non-Gaussian. Now we can do this analysis for sort of many regions, and we can make up Kappa index maps as we have done here. So again, in this image, the red is the coronal source, and then around that you've got the 2 foot point sources. And you can see we've only got a few lines here. This is because we were very careful with the analysis, and these were the lines that we were really sure were definitely non-Gaussian. But even though we only have a few lines suitable for analysis, we see a very interesting trend here. So we can see that the boxes or the rectangles that are closer to the coronal X-ray source have smaller Kappa indices than those that are further from the coronal X-ray source. The Kappa index seems to increase as we move away from the coronal X-ray source. So this is quite an interesting result. And we can also convert this sort of line result into a Kappa velocity distribution, as we've done in the figure on the right. And you can see that the lines and their velocity distributions have sort of larger tails than the assumed Maxwellian, which would be the red curve in this graph. Okay, so we can do a similar analysis for our cool line, or cooler line, IN16, which is formed at about 1 to 2 million Kelvin. Now we're looking at time during the flare just after the peak. And we can see we're looking at this region. We've got a little rectangle now, and it covers the northern ribbon. And this is a place where previously we saw a hard X-ray foot point as well. So we can look at the spectral line from this region, and again we have a similar result as before. We see that the blue Kappa Gaussian fit is a much better fit to the line than the orange Gaussian distribution. Again, it's able to fit both the peak and the wing, and we can see it's a better fit in terms of the residuals and hence the chi-squared goodness of fit. And again, we see a low kappa index of 3.9. So again, as before, we can then create a kappa index map at this time. And again, we're very careful with this analysis. We've only got a few points on this map, but again, they're quite interesting. We see definite non-Gaussian spectral lines sort of close to these ribbon features and close to where we previously had hard X-ray foot points. And another interesting result is that the kappa indices for the cooler iron 16 line are smaller than from the hotter iron 23 line. So the spectral lines for iron 16 are more non-Gaussian than those for the iron 23 line. Okay, so let me just summarize some of the main results of that study. So we indeed found non-Gaussian spectral lines in different parts of the flare. So in the loop top, and then also in regions close to where there were ribbons and hard X-ray foot points. As we might expect, the hot iron 23 lines were situated closer to the coronal source, and interestingly, they tended to move with the coronal source over time. And we also saw that interesting result at the peak of the flare, where the smaller kappa indices were closer to the coronal X-ray source. Next, we saw that the cooler iron 16 lines were situated closer to where we had hard X-ray sources previously and where the ribbons were situated. And interestingly, the iron 16 kappa indices were smaller than those of the iron 23. And they also didn't show so much of a systematic pattern as the iron 23 lines did. Okay, so once we had performed this study, the next step was to try and say whether sort of accelerated ions or non-Gaussian turbulence was the most plausible cause. So first of all, we thought about whether non-thermal ions could be produced in these lines in the flare. So we thought about whether these ions, these low energy ions, could exist in sort of the collisional environment, the high densities of the flaring plasma, and if they could exist, I guess, long enough for us to see them in this manner, in the spectral line shape. So we thought about, say, iron 16 ions interacting in an electron proton plasma. Now, for these low energy ions, we only really care about the ion proton interactions. The ion electron interactions become important at higher energies. So we can think about things like the collisional times and the ion thermal ionization time, as we've plotted here. So for different ion velocities and for different number densities that are sensible, for a solar flaring plasma. So if we take an example of where we've got a number density of around 10 to the 10, and we take an ion velocity of around 200 kilometers per second. So this would be one of the fastest velocities we might see in the spectral line profile before we sort of hit the background level. Then we can work out an ion thermalization time of about 0.01 seconds. Then it's sort of nice to turn this into thermalization length, which is a lot less than 1 arc second. So this tells us that if we're accelerating ions during the flare, these low energy ions, they're not moving anywhere. They're accelerated locally and they're producing their EUV emission exactly where they're accelerated. So this is quite a strict condition considering we saw non-Gaussian profiles at different locations throughout the flare. However, of course, we can think about this a bit more. And the nice thing about assuming, say, the ions had a kappa velocity distribution, for example, is that you can think of a kappa distribution as a sort of an equilibrium between acceleration and thermalization. So in this sense, you can think of the kappa index as a ratio of the acceleration time to the collisional time. And if you do this and you take the kappa values you found from your study, you use sort of sensible collisional times in the flowing plasma, then you can work out sort of a rough acceleration time, sort of less than 0.1 seconds, which again, if I'm honest, doesn't mean much to me at the moment. I was hoping to do sort of further work with this with modeling, but nevertheless, I think it's a useful parameter to be able to have. However, again, I'd like to say I think the fact that we're seeing these non-Gaussian spectral lines at different locations in the flare for different temperature lines maybe suggests that we're not actually looking at direct ion acceleration here, but maybe it's more plausible that we're simply looking at another diagnostic of turbulence in this flare, basically alongside the normal non-thermal broadening. And I think we've got other observations to sort of back that up. So again, if you fit the lines traditionally just with a Gaussian distribution, you would see an excess broadening, which suggests the presence of random plasma motions and turbulence. And also, most of the lines we studied, both for iron 16 and iron 23, once we'd accounted for sort of their rest wavelengths, we saw that they were all redshifted. They all showed small downflows of around 10 to 40 kilometers per second. And this could be suggestive that all these, the plasma is undergoing those small downflows that could eventually lead to sort of the onset of turbulence in these regions. And again, I think having this diagnostic of turbulence is very useful. But again, I think it needs a lot more work, and I'm hoping to do some modeling work on this very soon. Okay, so if we have time, which I think we've got, I'd like to mention something about another study that we did at the Sun, where we found the presence of non-Gaussian spectral lines in a coronal hole, basically at the base of the fast solar wind. So with my colleagues at Columbia, we analyzed Hanodi ice data from this nice polar coronal hole that we can see in the image here from the 23rd of April 2009. So there were basically 4 observations. They were all 30 minutes long, and they've been previously combined together for a previous study that looked at the non-thermal line broadening in this region. But in this region where you can see this little red rectangle, this is where we're going to look at the lines and where we're going to look at the basically look for non-Gaussian spectral lines. Now, the nice thing about this observation was that it's a full ice wavelength observation, which means compared to the flare cases, we had a lot of different spectral lines available for study. And here are just some of them. And in red, I highlight the ones that were suitable for line profile analysis. So you can see we ended up with 5 lines. I think they were formed over temperatures of about 0.5 to 1.5 megakelvin. Now, the main point of doing this study was for a number of reasons. Firstly, it was just quite interesting to see if we could see non-Gaussian spectral lines in the coronal hole. Secondly, I thought maybe looking at this data might help us understand the flare data in some way, because there's probably similar processes happening. And thirdly, my colleagues at Columbia, they're interested in looking at the fast solar winds, and they're interested in looking at where the sort of the non-equilibrium, non-thermal properties of the fast solar wind begin. Do they begin in the lower corona? Do they begin further out, for example? And we hoped these sort of remote observations could help answer this question. Okay, so I'm going to go straight into the data. So here is a nice example. So this is the silicon 7 line, and hopefully you can just see by eye that it's, without fitting, that it's extremely non-Gaussian. So this data is nice in the sense that it's off limb, so you don't have this large background that might hide the wings, for example. And you can see I've got this plotted over a log scale. So we're looking over 2 orders of magnitude here. Excuse me. And you can see that the orange Gaussian does not fit the line very well. And we have to use either a double Gaussian or a Kappa Gaussian fit to fit the wings and the peak together. And you can see that is a much better fit from the residuals again. Now, most of the spectral lines we saw in this region from the coronal hole look like this. And here's basically the 4 results of this study. So in the end, we ended up with 23 spectral lines that were suitable for study. Now, in these figures here, I plot at the top the integrated intensity, and at the bottom the kappa index versus basically position along the slit. So we're basically moving out away from the sun along here. So the grey region is sort of on disk, and then when you get to the dotted line, this is the limb of the sun, and then we're moving outwards away from the sun after that. So if we look at the bottom figure, for the lines that were particularly strong, so silicon 7, iron 8, then we could see for on disk that the kappa index seemed to increase, and then when you got to the limb, it seemed to basically become approximately constant. And then the other lines that we had, which we could see off limb, they showed similar kappa values as the other 2 lines. And so basically all the lines that we studied had very small kappa indices of less than 3, so they were extremely non-Gaussian. And they all had a value of about kappa of 2.3 off limb, which was quite interesting. And we think this is quite a nice result because, to the best of our knowledge, this is the first time that the ion velocity distribution has been sort of probed in this manner, close to the sun and at the base of the fast solar wind. Okay, so again, we did the same procedure, as for the flare case. We sort of asked ourselves what could be causing these non-Gaussian spectral lines. And we thought, because we had more lines here, we had 23, we had 5 different lines formed over different temperatures with different charge to mass ratios. Maybe we could look for trends. We could look at how charge to mass ratio or how temperature was changing with the kappa index, for example. But the short answer is, even in this study, we just really don't have enough lines to say anything conclusive. So again, for example, if we had fluid motions or plasma motions, we might expect them to affect all the ions in the same way. But if it was an ion thing, it might be different due to heating, for example. Alternatively, if you had a cascade of MHD waves towards smaller scales, then you might expect more efficient ion acceleration, and lower kappa indices for ions with lower cyclotron frequencies. But again, it was difficult to make any firm conclusion because we just still didn't have enough ions here, enough data. So again, we need to look for other studies where we can have more data, and then hopefully we can make a firmer conclusion. Another thing I'd like to point out here is I noticed I did something very stupid. So I've got this crying face next to the charge to mass ratio. When I was preparing for another talk, I realized that I'd worked this out incorrectly, and that's now published in a paper. So basically the trend is correct, but I got the charge wrong from the notation in my code because I was a little bit stupid. But the trend is correct, but the numbers are incorrect. So if you read the paper, just please realize that. Okay, so I'd just like to summarize the talk. So we found non-Gaussian spectral lines in flares and in active regions. and also at the base of the fast solar wind in the coronal hole. And in flares and in coronal hole data, we found these non-Gaussian spectral lines in different temperature lines. And in both cases, we think the causes of non-Gaussian line profiles are either due to non-Maxwellian ion VDFs, some accelerated ions themselves, or due to processes like waves or turbulence that can produce accelerated ions and other accelerated particles. And in many cases, there might be a combination of both. Now, following on from the flare observations, we look for non-Gaussian spectral lines in fast solar winds, and I think it's quite an interesting observation. It shows that remote observations sort of are useful for this type of study, and going to be complementary, I think, to in situ observations with Parker Solar Probe and with Solar Orbiter, which will be studying sort of ion VDFs that are closer to the sun than ever before, and trying to work out where these sort of non-equilibrium processes in the solar winds begin. So, what about the future? Well, I think this is an interesting perspective diagnostic, but to date, it's been hard to sort of single out a cause of non-Gaussian spectral lines. But hopefully, in the future, we have better spectral information, better instrumentation to be able to do studies of this type. So we've still got Hinode ice, we've still got IRIS flying, but hopefully. Sorry, excuse me. We'll have instruments such as DKIST. They'll be able to look at a lot of spectra from infrared lines in the corona with high spectral, spatial, and time resolution. Now, this won't be so good, of course, for flare studies, but this is going to be great for, say, coronal hole studies and studies of the fast solar winds. So I'm looking forward to analyzing that data. And then, of course, I think there is an EUV spectrometer on board Solar Orbiter. I'm not particularly familiar with this, but of course that might be useful alongside the in situ data that comes from these instruments. That might be good for looking at the solar wind and for flares. But I think this type of diagnostic tool and this type of study really pushes for sort of a new sort of EUV spectrometer that can study lines in the corona. So I'd like to finish there, and I'm happy to take any questions. Thank you.
Thank you, Natasha. It's very interesting talk, I believe. So thank you very much. We are open to questions and comments. So if you have fun, please go ahead and unmute your microphone. Jello, are you having a question?
Yes. Yes. Thank you, Natasha, for very nice talk, and you show us convincing examples of fitting with non-Gaussian versus Gaussian spectral profile. But I have a question. When you do this fit, did you take into consideration the distribution of the noise? Do you have a noise model for your data?
So I guess the noise comes from there's errors on the data, yeah, intensity errors.
The reason I'm asking is that from my own experience, when you try to fit a spectrum, the distribution of the noise in the spectrum is essential for determining the significance of the residual. So
yes.
I assume that if you did a least square fits using a K-power Gaussian model, you assume a Gaussian distribution of the noise. But I was wondering if you really studied the real distribution of the noise in this kind of data.
So I guess in terms of noise, we can only fit lines, I guess, that have a high signal. Does that answer your question? Yeah, noisy lines, it's impossible to determine the line shape, basically.
Okay. Anyway, I was curious, so I will read in more detail.
It's always anything to the line, yeah.
Okay, thank you.
Okay, more questions? Let me look through microphones. Lucas, no, you're muted, yes. Natasha, I have a couple of questions. I wrote down a few of them. So when you showed your kappa map for flares, it looks like it's more non-Gaussian in the loop-top source, which could imply that the acceleration side for ions is more or less the same as acceleration side for electrons. Is it correct observations?
The odd, well, what I thought was quite an odd observation, which initially made me question actually the data. Let me go back. Sorry, is that the Kohler line appears to be more non-Gaussian than the Hotton line, which I think is quite a strange observation.
Mm-hmm.
And at the moment, I don't know the causes of that. This needs a lot more work, and I think it probably needs some complementary modelling work to look at this properly, which again I haven't got around to doing yet.
And could you comment how like evolution of ionization states can affect all this interpretation? Is it important that ionization state can change for accelerated fraction of ions differently compared with thermal ions?
So again, I mean, that I don't know. I don't know how this would change with ionization state. All we have here is two different ions, yes, formed at different temperatures. I mean, it's all the information I have. So I guess at the moment I can't really answer that question.
Mm-hmm. Okay, and I have my final question. It looks like you are finding non-Gaussian shapes almost everywhere, in flares and non-flaring region and coronal hole.
Yeah.
Would it imply that the corresponding ion acceleration is ubiquitous, or what?
So that was one thing we thought about when we were looking at the interpretation here. So I mean, if the shapes are due to low energy accelerated ions, then it means we'd be seeing ion acceleration maybe in the corona and much lower down, which I don't know is kind of, well, it was, I guess, one argument against this being a direct diagnostic of ion acceleration, more towards maybe processes like turbulence. But again, I'd really like to do some modelling with this and to see what can happen. But again, I'm sorry, I haven't got around to that yet.
Okay, so I see raised hand from Lucas. So Lucas, if you have a question, just unmute your microphone and go ahead. Lucas?
Okay, can you hear me?
Yeah, I can hear you, but
Hello?
a little bit weak. Yeah.
Okay. All right. Hi, Natasha.
Hi.
It's very nice talk. Thank you very much. It's very convincing that that the turbulence are present. The only thing that when you come to modeling, I think we have to be a little bit more careful when we are touching turbulence. If the model that you are actually presented, or the sketch that you presented in order to project the data, had really the traditional loop where the turbulence were sitting inside the accelerator region and the rest was streaming. I think when you touch the modeling, I think we have to think again at the level of turbulence. If the entire loop is in the form of turbulence, so it can be accelerating particles all the way. It doesn't really focus on the top, and also hitting. The turbulence they're not only accelerate particles, but they are hitting particles as well. So I feel that when you start touching the modeling, predictions from a very, from a better sketch of the magnetic topology where these things are hosted, using some extrapolations, using other ideas, it will be very, very interesting addition and not really rely on the old-fashioned thing that we had in mind, where the top was everything happening there, and then we had this streaming particles leaving from there to go, the traditional thick target model. But anyway, but it's your next step, and I wanted to give you a warning that we should extend the modeling to accommodate this kind of new, turbulent situations, as because it can be more extensive participation of turbulence everywhere. As you discovered, turbulence are probably naturally coming from the convection zone, or photospheric turbulence are everywhere. So there is no surprise to me that you find them everywhere. The question is, what is the role of accelerating and hitting the particles, which is on the modeling stage that you're planning to do next. So good luck with the next step, which is very, very important too. Thank you very much.
Thank you. Thank you, Carl. I fully agree. I mean, even during a flare, you see signatures of non-thermal line broadening everywhere, not just in the corona.
Okay.
So it looks like that non-thermal ion acceleration might be more constant process than electron acceleration.
More constant process.
It's everywhere. Active region, coronal hole, everywhere you see this non-Gaussian.
Well, I think it's slightly more difficult to interpret in the coronal hole because it's a sort of collisionless environment. So indeed, you could have low energy accelerated ions existing quite happily. I think in flare conditions, if you're heading down towards the transition region, you're getting to higher densities. It's maybe harder to keep low energy accelerated ions accelerated to sort of produce these line shapes. So in that sense, I'm not sure it's a direct diagnostic of ions, but just of processes that could either produce acceleration or heating, as Lucas said.
Okay, thanks. Any other questions? Let me see on the participant list. It looks like everyone is muted and no one has raised a hand. So if so, let me thank our speaker again, and let me thank all our participants. Next meeting, next webinar will be in 4 weeks with a speaker from Switzerland, Marina Battaglia. So thank you very much. Thanks, Natasha.
Thank you.